Hello, everyone. On behalf of the team, I, Akun Raman, welcome you all to our presentation titled Gang of Eight, a Defect Taxonomy for Infrastructure as Code Scripts. Our research related to defect taxonomy for infrastructure as code scripts was in collaboration with Ifat Farhana, Chris Parnin, and Laurie Williams from NC State University. Infrastructure as code scripts, or ISC in short, is the practice of automating the process of configuration management and computing infrastructure provisioning. Automation is one part, but it also requires the implementation of good software engineering practices such as version control and quality control, such as applying tests, applying linters, etc. There are multiple tools to implement the practice of ISE, which are being used by different organizations such as Mozilla, Ambit Energy, ICE, which stands for Intercontinental Exchange, and NASA. All of these companies have reported benefits of using IAC. For example, for Mozilla, the manual efforts were reduced by 99%. Ambit Energy experienced the deployment frequency increase by a factor of 1200. ICE were able to reduce the provisioning time from 1 to 2 days to 21 minutes, and NASA was able to reduce its patch release time from multiple days to 1 hour. Despite all these benefits, defects in ISE scripts are prevalent. So for example, we notice anecdotal evidence where AWS and GitHub experienced wide-scale outages due to defects in infrastructure as code scripts. As multiple teams and software and service providers depend on these services, if outages due to ISE scripts happen, then that causes a cascading effect on everyone dependent on these services. So it is important to mitigate these defects and improve the quality of IC scripts. And not only from this anecdotal evidence, we also see that even on online forums, there is a discussion and a need to talk about or understand the defect categories for Puppet scripts or infrastructure as code scripts. So for example, in this particular Reddit post, a practitioner discusses the fact that the practitioner wants to implement Puppet in his or her organization, and before adoption, the practitioner wants to be aware of the quality issues related to IC scripts. So both the scientific need and the practitioner need motivated us to conduct our research. The goal of our paper was to improve the quality of IC scripts by developing a defect taxonomy through qualitative analysis. We answered the following research questions, namely RQ1, which focuses on the categories and the taxonomy itself. RQ2 focuses on the practitioner perception, that is, to what extent practitioners agree that our defect categories make sense, and then the quantification of the frequency of the identified defect categories using an automated tool called ACID. So for RQ1, what we did was we looked into open source repositories maintained by OpenStack, collected comments related to defects. So these are comments which has commit messages that include keywords like bug fix, bug, faults, etc. Then we looked into these commits for bug report IDs as well, and then we extracted those bug report summaries. And from the combined message, we systematically applied open coding to derive categories, which in turn became a taxonomy. For practitioner perception, we looked into the same repositories, mined the same repositories for email addresses for practitioners and sent them survey. So this was a survey where we posted questions to see if practitioners actually agree on the identified defect categories. And finally, for RQ3, what we did was we wanted to analyze the frequency of defect categories at scale. So constructed an automated tool called Automated Categorizer for Infrastructure as Code Defects ACID. And the tool was built using the information provided in defect-related commits, the commit messages themselves, and the code elements that are being changed. From that, we abstracted them into rules using dependency parsing. Details can be found in the paper. After that, what we did was we systematically filtered 3.5 million repositories from GitHub, the online social coding platform, as well as from organizations who have made their IC scripts open source, namely Mozilla, OpenStack, and Wikimedia. So all our data sets were Puppet scripts, and we ran our tool ACID on commits in which Puppet scripts were modified. And from there, we quantified our frequency. So our results were, first, we identified 8 defect categories. 4 of them are conditional, configuration, dependency, and documentation. So conditional defect, the category conditional defect corresponds to erroneous logic and or conditional values. Configuration data defects corresponds to data for storage, file system, network, user credentials, and caching systems. Dependency defects corresponds to artifacts for which execution of a public script is dependent upon, and documentation corresponds to source code comments and maintenance notes. The other 4 categories were idempotency, security, service, and syntax. Of the identified 8 categories, we observed that compared to prior literature, idempotency is the most unique one to IAC. And idempotency refers to when multiple executions happen for a public script, the results are not the same as the first execution. From our survey results, what we observed that idempotency-related defects was the most dominant category, and service-related defects were the least dominant category. We also noticed interesting insights from the survey responses. So, for example, we observed that practitioners have varying perceptions on what are important and what are not. So, for example, one practitioner said that idempotency and conditional defects are the 2 key ones, whereas debugging dependency loops is an important category for another practitioner. We also observe practitioners to mention other types of categories that they think are defect categories, such as maintainability, parallelism, and scalability. This might be of interest of future researchers who are conducting defect-related research in ISC. We observed that configuration-related defects is the most frequent one across all the 4 datasets compared to the other 7 categories. And even in our temporal analysis from 2005 to 2019, we observed that configuration data defects always remain the dominant one across time. In short, our findings can have implications for practitioners, researchers, and educators. So practitioners and researchers can use our findings and our quantified frequency as a benchmark to compare and contrast how frequently different categories of defects are compared to other types of software, as well as IEC software that are being used in different proprietary domains. For educators who are teaching DevOps-related classes, the presented examples of different types of defects can be discussed in the classroom and integrated. Our taxonomy can be useful for researchers who focus on automated program repair, as it might give them interesting clues on how to generate automated fix for different types of defects for IC scripts. In short, we talked about the importance on why we need to systematically categorize defects and construct a defect taxonomy. We discussed how we constructed our defect taxonomy and what were our findings. We identified 8 categories of defects. Next, we constructed an automated tool to find defect category frequency at scale. We also discussed the implications of our paper for practitioners, researchers, and educators. If you have questions, feel free to reach out to me, and have a great ICSI conference.